Hello everybody, welcome to session 5. So in the last session we saw how to present the rainfall data and how to estimate the missing rainfall data. So in today's session I will be talking about rain gauge density and why is this rain gauge density important. So moving on to session 5, let me talk about rain gauge density. So the catchment area of a rain gauge is very small compared to areal extent of a storm. It becomes obvious to get a representative picture of a storm over that catchment. The number of rain gauges should be as many as possible. So what is this? If there's a catchment area, if it is a large catchment area, then I just cannot have 2 or 3 rain gauge stations. I need to have more number of rain gauge stations so that I will get a true representative, which means the exact value of rainfall or that precipitation can be calculated over that particular catchment area. So the more number of rain gauges, the more accuracy can be arrived at. So on the other hand, again, the topographic conditions and accessibility restrict the number of rain gauges to set up. So I cannot go and set up at every point. Again, it should be easily accessible. The topography of the land is very, very important. It should be a plain, flat land. So all those conditions come into picture whenever we are installing a rain gauge station. But still, considering to have a true representative, it's always better to have more number of rain gauge stations. And we have should place them so that easily it will be accessible, recordable, and true representative can be got. Hence, one aims at optimum number of rain gauges from which accurate information can be obtained. So, from practical considerations, the Indian Meteorological Department, uh, as per IS Indian Standards 4987, has recommended the following rain gauge densities depending upon the type of area. So wherever the catchment area is plain, we can have one station for 520 kilometers square. If the areas have an average elevation of 1000 meter, then one station per 260 to 350 kilometers square. And wherever there are hilly areas, predominantly hilly areas with heavy rainfall, you can have one station per 130 kilometers square. So in hilly areas, we need more number of rain gauge stations. So moving on to the next topic, it is optimum number of rain gauge stations. So if there are already some rain gauge stations in a catchment, the optimal number of rain gauge stations that should exist to have an assigned percentage of error in the estimation of mean rainfall is obtained by statistical analysis. So this statistical analysis will give us minimum how many number of rain gauges have to be installed. So the number of rain gauge stations, that minimal number which should exist so that the percentage of error assigned there in the estimation of that mean rainfall is minimum. That is known as optimum number of rain gauge stations. And it is calculated where we use the formula n is equal to CV divided by E raised to whole square. So where n is optimum number of stations is equal to E allowable degree of error in the estimate of mean rainfall if there are n stations in the catchment. Each recording rainfall values, that is P1, P2, P3 up till Pn in a known time, the coefficient of variation is known as CV. So this formula is always used to calculate the optimum number of rain gauges. N is equal to CV by E whole square. CV is coefficient of variation of rainfall based on the existing rain gauge stations, and E is allowable percentage error because there will be slight error. So they give us this option as allowable percentage error in the ultimate uh, where estimation is done on the basic mean rainfall. So again, further, CV can be computed, that's coefficient of variation of rainfall. It is computed where first we will determine P bar, where all the precipitations in that particular rain gauge station, in that catchment area at different rain gauge stations, 1, 2, 3 or A, B, C, D is P1, P2, P3, P4, and up till Pn. So we add all those P1, P2, P3, P, summation of that P divided by n number of rain gauges If it is 5, 8, 10, divided by that number of stations. If it is 8, P1, P2 up till P8 divided by 8 will give us P bar. So N is number of rain gauge stations existing, and summation P is the total rainfall, that is summation of all the normal annual rainfall values, precipitation values in that particular catchment area. Then we calculate mean of the squares, that is P bar square, summation P square by N. We arrive at that value, and then we calculate using this formula standard deviation is equal to n by minus 1 P bar whole square minus P bar whole square. So that will give us standard deviation. Therefore, CV is nothing but coefficient of variation is 100, standard deviation divided by P bar. So we will have calculated P bar here. We will have calculated CV is equal to 100, standard deviation we will have calculated here. 100 into this standard deviation divided by P bar will give us CV. Percentage error will be known. So directly N is equal to CV divided by that percentage error, the whole raised to square, will give us optimum number of rain gauges which are required in that particular station. In this way, we'll calculate the optimum number of rain gauges. Next, we will study about double mass curve. So what is this double mass curve? The various tests for consistency of rainfall have to be done, whether it is consistent or inconsistent. What is this consistency? It means uniformity. Whenever anything is recorded, there should be a uniformity. If one rain gauge shows 5 centimeters, the neighboring rain gauge shouldn't show 10 centimeters. It cannot vary to that extent. So it should be consistent. There should be a uniformity. So if it is inconsistent, we have to determine it. And that is determined by this double mass curve. So let me talk about it. If the conditions relevant to the recording of a rain gauge station have undergone significant change during the period of record, then inconsistency could arise in that rainfall data of that record. So it has undergone some change. Therefore, the results are not consistent. So what those changes are, or why those changes have occurred, they can be various reasons. So the consistency of a rainfall record is tested with double mass curve. So double mass analysis is done, and that is known as double mass curve. This method compares the cumulative rainfall or annual rainfall with the stations of X with those of a reference station. That reference station is usually the mean of several neighboring stations. So why this inconsistency in that recording from that particular rain gauge station arrives? Why? Because they might have shifted that rain gauge station to a new location, or the neighborhood of that station might undergone a markable change or remarkable change. Something might have been constructed there. There might be some vegetation there, or there might be some building there, some construction that has led to some inconsistent result, or change in the ecosystem because of calamities, that is natural calamities. It can be forest fire, volcanoes, landslide, anything. So that also may lead to inconsistency in recording of the rainfall data. Occurrence of observational error from certain date. So a person will have recorded or written down that recorded rainfall with some mistake, and that mistake will have been followed. It will have been continued from that date. So that observed error is there. So in this way, errors will have occurred. In this way, recording will be wrong, and this leads to inconsistency in that rainfall record. Hence, we need to check this inconsistency where the recording is done, and that inconsistency of that record is done by double mass curve technique. This technique is based on the principle that when each recorded data comes from the same parent population, then they are consistent. Because from the same rain gauge station, from the same parent population, what we mean to say is from the same area, from the same station, it has been recorded, then why inconsistency has arisen? So we use this double mass curve technique, and let us see how the procedure works. So here, a group of 5 to 10 base stations in the neighborhood of the problematic station X is selected. So the problem area is X. So surrounding 5 to 10 base stations in that neighborhood are selected. The data of annual monthly mean rainfall of the station X and also the average rainfall of that group of base stations covering a wrong period is arranged in reverse chronological order. So it is not in increasing order. It is not from old to new, but new to old is arranged. So when we collect the data, we usually get from 1960 to 1990. So it will be written as 1960, 61, 62 up till 1990. But now, reverse chronological order, we need to arrange it where we the latest comes on the top. 1990 is written at the top, and then 90, 89, 88 up till 1960 it will be written in a reverse chronological order. So once that is done, this point is very, very important in this double mask curve where latest data will be at the top. In others, the top will be the oldest, then we go on putting in increasing order, that is old to new, but here it is new to old. That is known as reverse chronological order. So the accumulated precipitation of station X and the accumulated precipitation values of average of group of that base station, they are calculated starting from the latest record. Then values of summation Px are plotted against summation P average for various consecutive time periods. Then that decided break in the slope will arise where there is inconsistency. And that resulting plot indicates the change in precipitate regime of station X beyond that period of change of regime is corrected by using the relation PCX is equal to PX into MC by A. So where PCX is corrected precipitation at any time period T1 and station X, and PX is original recorded precipitation as time period T1 at station X. So MC is corrected slope of the double mask curve, and MA is original slope of the double mask curve. So let me show you all the figure. Now let us see how it is plotted. So this is accumulated precipitation of the station X, summation PX, and this is average accumulated precipitation of neighboring stations, P average. Okay, then we plot those readings corresponding to the years. So 1990 at the beginning, that is the newest, till 1980 to 81 it goes on. Then we start getting these points corresponding values of accumulated precipitation in this particular year. Then against Px against P average, summation Px against P average is calculated on that tabular column. Then after that, those values are plotted here. Then when we join, this has to go in a straight line like this. But here it will have moved. There will be a break in this line, which shows the inconsistency has occurred in the year 1987. So we need to find the correction factor. So we just extend the straight line here. So this is the actual slope. So it is written as A, or MA also is given. This is actual slope and this is the corrected slope. So this is given as C because actual, when we draw the points, you can see here. So from this point at a certain year when we take, this gives us actual. And this extended one is the corrected slope. We have corrected it by extending it. So this gives C. So this is MA, MC. So the calculations are done using PCX is equal to PX into MC by MA. So PX is corrected precipitation at any period time. PX is the original recorded precipitation. MC is corrected slope of double mask curve, that is called, because we get two curves. So it is called double mask curve. And MA is original slope, where exact values will be drawn and we get that original slope MA. This extended will give us MC. So into MC by A into PX, that is original recorded precipitation, will give us the final corrected precipitation at that particular station, which has undergone some remarkable change and there is some inconsistency which has occurred at that station. So this way we use the double mask curve to determine the inconsistency which has occurred, and we find out the consistent result using this correction factor MC by MA. Thank you.